Welcome to the second session on Verilog Kickstart. In this session, we will be seeing the different design styles, otherwise known as design abstractions in Verilog. So, if you examine the different design styles supported by Verilog, Verilog support 4 of them. One is algorithmic or behavioral style. Second one is data flow style. And the third one is gate level or structural style, and the fourth one is switch level or transistor level style. Okay, so when you are writing a code for synthesis, we may be using a combination of all these things in a legally appropriate manner. And also synthesis, actually we call the code written for synthesis RTL code, wherein RTL stands for register transfer level, wherein the code is described in such a way that how data flows between different registers. So this particular way of writing the Verilog descriptions that can be synthesized is called register transfer level. Okay. Now if you see what is behavioral modeling, it is more of algorithmic in nature. On certain occasions, the designer has a very complicated algorithm to implement, but he is not sure about what would be the gate level structure of it, neither how data flows between different registers. All what we could imagine in such a complex case could be a step-by-step procedure or kind of algorithm. So if that is what is in hand, designer can go about writing it in a behavioral style, wherein only the functionality of the circuit need to be described. The synthesis tool is later made to take up the responsibility of inferring the correct logic and thereby creating the appropriate netlist. Okay. So behavioral style is both used for synthesis as well as simulation, but it is something to be carefully used. Otherwise, there is a risk that the synthesis tool will infer incorrect logic, which may ultimately lead into a chip failure. Okay, for example, what you see here is a language independent representation of a shift register. You can see that while examining the behavior, you can see that there is a mode control kind of pin called switch left, and if that is high, the output is nothing but the left shifted version of the input, or the output is nothing but the shifted version of the previous copy of itself, else it is shifting it in the opposite direction. So it's a bidirectional shift register if you look at this snippet of the code. So this kind of representation of the functionality of the circuit without direct mentioning about the structure is called behavioral modeling. The other way, as we called it, structural modeling, is basically building up a higher level component by instantiating lower level components. For example, you want to make a 16:1 multiplexer, you know it can be made up of a series of 2:1 multiplexers attached in a particular format. So lower level component here could be 2:1 multiplexer. They are assembled or stitched in such a way that finally a 16:1 multiplexer is implemented. Okay, so this is basically the preferred style because it calls out for specific hardware. So the benefit of doing structural modeling is that once structural modeling is done appropriately as per the structure, the possibility that the synthesis tool will infer a wrong hardware is less, which is not the case with behavioral modeling. Okay, because here we are straight away telling the tool not the functionality but the actual circuit structure which it is supposed to implement. Now if you look at where these different abstractions come into play, if you want to design something at the component level, which is the most optimized performance delivering component, so in such a case we will go for transistor level modeling, but hardly this is in practice because of the complexity of the VLSI circuit involved. So switch level modeling or transistor level modeling is it's like kind of non-existent in real practice. The next level is called gate level modeling. It is a highly preferred style. So whenever you are working in a product company kind of thing, most of their product will be reaching maturity. So in that case, they will be having a structural kind of descriptions, which is the most foolproof way of taking it to synthesis. The other styles include RTL way, or say data flow modeling, wherein we are specifically telling how data flows between different components. At the top level, that is at the system level, and often when the algorithm is complex, say a DSP algorithm, those kind of things, when there are a lot of computational complexity involved and it's more of algorithmic in nature, we go for behavioral modeling. So if you look at, when you are writing things in behavioral modeling, the design time is very less, but it comes at a cost of higher implementation risk because of the logic misinference problems. Now let us examine what are the different styles in practice. As I told, any hardware module can be made to be described in any of these styles. Let us take one simple example and slowly we will add complexity to it so as to understand the design abstractions. For example, to start with, let us try out a simple 2:1 multiplexer as shown in this particular diagram. It has two input A and B and one select input S. When S is 0, it is supposed to drive A to the output, and when S is 1, it is supposed to drive B to the output. So that is the specification. We are trying to write it in different styles. Let us start with a simple assignment operator, which is continuous assignment. So here, as normal, we write the keyword module, then we will write the module name, then we list out all terminal ports being A, B, S and out in whatever order we would like. Then we will describe the input port, which are A, B, S, all are scalar ports. Then we will describe the output port out. Then we have to create this particular thing in a data flow manner. Data flow manner means using operators. So we have to have the expression for output. The expression for out here is out is equal to A S bar plus B S. So we require a signal called S bar, so which has to be created because there is no S bar signal in the terminal port list, and we know S bar is nothing but tilde of S. So we are writing assign S bar is equal to tilde of S. As I already explained, tilde operator is used for negation, bitwise negation. So whatever value you are feeding in S, it will get complemented and will be fed to S bar. So once S bar is there, we can assign the output as out is equal to A ampersand S bar ORed with B ampersand S. Because there would be operator precedence, that is, we are not sure whether AND operator will work ahead of OR operator. If you are not sure about it, we put a bracket to override the precedence. So whenever there is a bracket, it gets priority. So A will get bitwise ANDed with S bar, and B will get bitwise ANDed with S, and the OR of these two things will be assigned to output, materializing the sum of product expression. So we are done with the functionality in the data flow way. We are ready to write N module and thereby terminate the program. So this is the data flow model, because here we are explaining how data flows between different variables or registers with the help of operators. Now this is simple assign operator. We can also use conditional operator for this purpose. Conditional operator, as I already explained, comes with a syntax like this. The destination variable is assigned with a condition to be tested, a question mark, a true value, false value. So the same thing we are trying to adapt here to form this 2:1 multiplexer. We write the module name, list of all terminal ports. We describe the input port A, B and S bar, describe the output port. Then we can write a simple conditional operator statement, assign. The destination variable here is out, is assigned with what is the condition to be tested. Select signal is the condition to be tested. Accordingly, one of the input will flow to the output. So S, a question mark, when S is 1, what should be in the output? That should be written first, because the syntax is the condition to be tested, question mark, true value, false value. So here, when S is 1, according to this specification given, B should be going to the output. So I am writing S question mark B colon A. So the meaning of this is whenever S is 1, B will go to the out. Whenever S is 0, A will go to the out. Okay. So that completes the specification in a single line. You are good to write N module. So this is also data flow modeling because it is using operators only, and it is using conditional operator, which is a special type of conditional operator. So you please understand, whenever you find a conditional operator, it will get synthesized to a multiplexer structure. Okay, we may not be describing a multiplexer all the time. We may be describing a microprocessor or something, but whenever the compiler see such a statement, it get inferred to a multiplexer logic. So that is about conditional operator. Now let us see how the same multiplexer can be written in behavioral modeling. As I already pointed out, in behavioral modeling there are multiple constructs. One is using the if-else and the other one is using case statement. We will see if-else first and then we'll move to the case. So while using if-else, we have to write module name, list of all terminal ports as normal, declare the ports, declare the output port. One important difference you please notice here. Earlier I have written output out. Here I have added a word reg, which is a keyword. I will tell you the reason for that. Please keep it in mind. Then what I should do is I should write an always block. Okay, so I am writing always at the rate, then I put a bracket and list out all the ports, the changes of those ports which should be sensitive to, the always block should be sensitive to the changes of these signals. So this list is called sensitivity list. So whenever you are trying to describe a combinational circuit like this, please be sure to insert all the ports which you have declared as input into the sensitivity list. So suppose you are describing a hardware having say 100 input and you forget to add each one in turn, then what you can do is you can put a asterisk mark here inside the bracket. It will serve as a wildcard character and the compiler will automatically insert all the ports which are declared as input into the sensitivity list. So the meaning of this is, whenever the value of A or the value of B or the value of S changes, this loop is entered. This always loop is entered. So always loop is used to model a set of activity which is happening in a continuous looping fashion in a hardware. Okay, so once this loop is entered, I am writing a begin and end. A begin and end are nothing but something similar to opening braces and closing braces in C. It is just used for grouping a set of activities together. Okay, then inside which I am writing if S. If S means if S is equal to 1. You may either write if S double equal to 1 or you can simply put if S. Both means one and the same. So if S, what should be the output? According to my specification, if S is equal to 1, output should be P. Else, my output may be A. So that is what I accomplished here. So whenever I have written a begin to start grouping the statements, once it is done, I should put an end. Then I am good to write the end module and terminate the program. So now let me explain you why I have written an additional keyword here called reg. So you look at here, the value of out is getting updated only when the value of either A or the value of B or the value of S changes. Until and unless it changes for the next time, the variable out should retain its value. So all such variables which are supposed to hold the value temporarily must be declared as register data type. Okay, so to cut it short, or as a rule of thumb, you can remember it this way: whenever you have a variable which is assigned inside a always block or an initial block, or whenever you have a variable assigned within a begin and end, it must be declared as register data type because it is not getting updated every instant of time. Okay, earlier you can see that in the earlier example, you can see that the variable called out is getting updated at every instant of time because of the assign statement. It is continuously assigning the value of the expression of the right hand side to the left hand side. So any variable which is being continuously driven is of net data type. So whenever you have net data type, the keyword to be used is wire. But I have purposefully not used the keyword wire because wire is the default data type. So if the compiler happen to see a variable which is not assigned with any data type, it will be read as wire only. So I am just riding on the luxury the compiler gives me. but that is not the case with sequential logic. In sequential logic, whenever you have a variable, not sequential logic, that is not the case with procedural assignments or sequential assignment. Whenever the variable has to is supposed to hold the value temporarily, it must be explicitly declared as having the type register. Okay, and what's the rule of thumb? You find any variable assigned inside always block or initial block, which are two procedural blocks in Verilog, that variable must be REG. Okay. Now let us see how the same can be accomplished in behavioral modeling, but this time using then another construct called case statement. Okay. So case statement, initial few lines are exactly the same as in if statement. Then you have to write an always block, the same sensitivity list. After begin, you use a keyword called case, and inside bracket you mention the condition to be tested. Here the condition to be tested is S. Okay, and you list out all the possible values this S can take. S can take 1 dash be 0, S can be 0 or 1. Okay, if it is 0, the output value should be A according to my specification, so I am writing it here. If it is 1, the output value should be B. Okay, I am also writing another keyword called default. So what is the purpose of default? Whenever you are writing a code for synthesis, it is always better to write a default. So what defaults does to my synthesis tool is that it tells explicitly to the tool if none of 0 or 1 happens to be in the select input. The user is supposed to give either a 0 or a 1 here. But if the user is not competent to understand that, or if there is some voltage, spurious voltage, or there is some attenuation happening with the S, a 0 given may read a higher value, or a 1 given may not read like a 1. So in that case, what your hardware should do, that is mentioned by another keyword called default. I am writing that if the user is not giving 0 or 1, let the output of my multiplexer be 1 dash BX, be in a high impedance state. Okay, so this is not part of specification, I have added it myself, but this is a good practice when you are writing Verilog descriptions for synthesis purpose, because it avoids a lot of inference issues otherwise. Okay. So that is about behavioral modeling using if statement as well as case statement. Now let us see how the same multiplexer is implemented using structural modeling. To implement its structural modeling, we need to understand what is the structure of the circuit which we are trying to implement. From this specification, it is clear that the expression for output is A S bar plus BS. So the same thing is materialized here. You can see that the out is nothing but A. So this is slightly not like this. It is B here and A here. So it should be A S bar. It should be read as A S bar or BS. Okay. This structure you please read this as A, so that it is A S bar or BS. Okay. In the case of this particular multiplexer. So here what we have to do is everything normal. We have to write module name, list of all terminal ports, declare the port as input as well as output. Then what you have to do is you have to instantiate the logic primitive. So by this what I mean is, in Verilog, because it is meant for describing digital hardware, all the basic gates are made available in a pre-compiled form in the library. So we simply have to call these gates. We don't have to describe it over and over again. Okay. So there is a conventional way of calling or instantiating these gates, that is called logic primitive instantiation. And the syntax for that is, first we have to write the keyword for the gate which we want to instantiate. So I am writing not 1. Then I am writing, so first not is the keyword, second not 1 is the instance name or the user given name. I can give even my name. This is just one indicative name I have written. When you are naming like this, please take care not to leave any space between not and 1, because not is a keyword. Okay. So not 1, then I am writing S bar comma S. So the meaning of this is, Whatever value appearing in the S, it will be reaching S bar as the knotted version of it. So whenever you are instantiating logic primitive, the output port is what you write first, followed by the input ports. In this case, there is only one input. For certain gates, there can be multiple inputs. Okay, so I have accomplished this particular NOT gate now. Now I will do instantiate the AND gate. So AND is the keyword, AND1 is the instance name or the label, and the output of my first AND gate is net1, and the inputs are, please read this as B and S because there is a small error in this slide, so it's B and S are the inputs. Similarly, for the next AND gate, it is AND2, and the output of that AND gate is net2, and the input should be A and S. Okay, AND2, the output is net2, and the input must be A and S. So the input should be A and S bar. For the first AND gate, the input should be AND1. For first AND gate, the input should be net1 A comma, it can be B comma S, and for the next AND gate it should be A comma S bar. Okay, so once it is done, I am ready to instantiate the OR gate. The keyword is OR and the instance name is OR1, and the output should be driven with net1 and net2 as the two inputs. So this is the way logic primitives has to be instantiated. The only correction which you need to apply here is, please label this first port of AND1 gate as B and the port of AND2 as A, and also add here S bar. So similarly, we have the freedom to instantiate other logic primitive gates. So far we have seen AND, NOT and OR. Similarly, if you want a buffer, BUF is the keyword. If you want an XOR gate, XOR is the keyword. NAND is the keyword for NAND gate. NOR is the keyword for NOR gate. XNOR is the keyword for logical exclusive or inverted gates. Okay. Now, to impress upon the design abstractions, let us extend our complexity to a 4:1 multiplexer. So 4:1 multiplexer, the specification given is like this. It has 4 data inputs, I0, I1, I2, I3, and 2 select inputs, S0 and S1. They are connected in such a way that when S0, S1 is 0, 0, I require I0 in the output. When S0, S1 is 0, 1, I require I1 in the output. When S0, S1 is 1, 0, I require I2 in the output. When S0, S1 is 1, 1, I require I3 in the output. So the sum of product expression would be out is equal to I0 times S0 bar S1 bar plus I1 times S0 bar S1 plus I2 times S0 S1 bar plus I3 times S0 S1. All these plus should be replaced with OR operator, and all these product terms should be having the AND operator as far as the logic implementations are concerned. So now let us see how to write it in using conditional operator, then behavioral statements, as well as using gate level primitives. To start with, let us discuss with the conditional operator. So as normal, we have to write module name. Here I have written module 4:1 multiplexer underscore DF to indicate and its data flow modeling. Any name I can give. Then I have listed out the ports. The ports should be I0, I1, I2, I3, S0 and S1. Please strike this off and use I0, I1, I2, I3, S0 and S1. And the input ports should be declared so. And there is only one output port to be declared, that is out. Now we can use conditional operator in a nested way, that is one conditional operator within the other. So here what we do is we have to write assign the name of the destination variable which is out, then write the first select condition. Okay, so in this specification the first select condition is S0, then comes a question mark, then we should write a true value colon false value. So for the true value we put a bracket, for the false value let us put a bracket. So inside the true value we have to check for one more condition in this case, that is S1. If S1 is also true, that indicates the condition 1 1. So if it is 1 1, we require I3 to flow to the output. So we write here I3. So the meaning of this is, whenever the value of S0 is 1, we reach here, we check for S1. If S1 is also 1, we reach here. That is on 1 1 in the select inputs we get I3. Suppose on the other hand it is 1 at S0 and 0 at S1, we reach at I2. Okay. Similarly, when S0 is 0, we straight away reach to the false part of the first conditional operator. Therein we check again S1. If S1 is true, it represents the condition 0 1. So in that case we require I1. Okay. Similarly, if we get 0 for S0, we reach here and we check for S1 and we get 0 for that also. That represents the condition 0 0. We must be using I0 to be connected to the output. So that is what is listed here. So conditional operator, when used in a nested flow, combines a lot of things together. In a single line we are able to implement this 4:1 multiplexer logic. Okay. So we require some correction here. Please list out these input and output ports, that is the terminal port list here. The terminal port list to be added is I0, I1, I2, I3, S0, S1. That should be residing in this particular bracket. So that's about the description in data flow modeling using conditional operator. We are going to write the end module part of it. So this is data flow because we are simply using assign statements and operators. We are not calling in any gates. We are not using always block or initial block. So it's a pure data flow modeling using conditional operator. Now let us see the behavioral part of it. So in behavioral modeling, we are trying to write it using if else statement. Okay, if there are multi-way branching, if else may not be sufficient. So the usage is if else if else. I'll show you what exactly it means. So as normal we write module name, then it's behavioral. You have to list out the ports as I0, I1, I2, I3, S0, S1 and out. The input ports are so and the output port is out. Then I am writing always a list of all input ports. Okay. As I told, if you are reluctant to put it, you can write it as a star inside the bracket, which is a wildcard character. So whenever the value of I0 or I1 or I2 or I3 or S0 or S1 changes, this loop is entered. So inside the loop, what we are doing is we are checking the possibility of different cases with the help of concatenation operator, which I already explained. So if inside bracket one condition to be written, I have written the concatenation of S0 and S1. Both S0 and S1 are 1-bit variable, as you can see here. When you concatenate it, you get a 2-bit variable. So it is equated with 2-B00. So if the select signals are 0 0, this condition should be true. So in that case, we require out to be fed with the input I0. Okay, now suppose if this condition is not what is there in the input, it goes to the else if part. Okay. Therein you are checking the next condition, that is S0 S1 is equal to 0 1. If it is 0 1, we require I1 in the input, in the output. Okay, so such an assignment is made. Similarly, if S0 S1 is 1 0, we require I2 in the output. When S0 S1 is 1 1, we require I3 in the output. Okay, so this particular thing explains the all legal conditions which we require our multiplexer to work with. But as I told, there is a possibility that the user ends up giving a non-legal input or illegal input. That is, the user input may not be 0 0 0 1 1 0 1 1 occasionally due to certain issues. So to deal with that, we write an else part. So the else here is equivalent to default in the case of case statement. Okay, so if though we see here 1 2 3 4 5 lines or so, if else is a single statement. So it is not a must. We must write begin and end. Begin and end are used for combining multiple events that happen sequentially. But don't hurt to give that as well. If you would like to give it a more structured view, you can always add a begin and end. It just serves the purpose of opening braces and closing braces. Anything which happen within begin and end happens sequentially. Okay. So that completes it. So you can write AND module. So now here also you please look, I have written the output out as a register data type, because as you can see the changes into the out variable is happening only on changes in any one of the input. Till the next time one of the input changes, it has to hold the value, and the reason why it is declared as REG. Now the same thing using case statement, most of the things are the same. Module name, list of all terminal ports, input and output port declaration, then always begin, but instead of if we write case, and we use the same concatenation operator. So when you are clubbing two scalars, we get a 2-bit vector, and the possible all alternatives we are listing it out. So here you please be careful. Here you may understand the importance of giving 2-, because if you are not giving 2-b here, this 10 may mean 10, because the default base in number system is decimal. So it's very important that you give 2-b so that the compiler knows for clear it's a 2-bit number to expect from the input, and it should be in binary format 10. Okay, so when the user gives any of these inputs 0001, 1011, the corresponding output will be given to the output. Also I am writing an default statement and feeding the output with a high impedance value or unknown value according to my interest to be flowing to the output. So whenever I write a case, I must ensure that I have written an end case. Okay, and a begin should have an end, a module should have an end module. If you happen to miss any of this, the compiler will throw you an error. So that is about 4:1 multiplexer in behavioral modeling using case statement. Now let us also see the structural model of it. As we already explained, to know the structural, to write the structural description, we require the structure. To get the structure, we require to have the expression. So the expression for 4:1 multiplexer, as we described earlier, is out is equal to I0 S0 bar S1 bar ORed with I1 S0 bar S1 ORed with I2 S0 S1 bar ORed with I3 S0 S1. So this same sum of product expression is materialized here. There is an S0, there is an S1, there is an S0 bar, there is an S1 bar. So these 3 input AND gates can be seen here with the corresponding input. For example, you look at AND 1, the inputs are I0, S0 bar, S1 bar. So does the other 3 AND gates. Similarly, all these 3 input AND gate output can be ORed. Instead of using multiple OR, we can use a 4 input OR. That is one charm in a hardware description language. You can have a gate having even n inputs. Okay, so the whole of this plus symbols are clubbed into one 4 input OR gate here. Okay, so this circuit we need to convert into a description as done earlier. Module name, list of all ports, declaration of the input ports, declaration of the output port. Also I have declared S0 bar and S1 bar as wire. Even if we don't write it, nothing bad will happen, because as I told, wire is the default data type in Verilog. Just to avoid the confusion to the listeners from where S0 bar and S1 bar appeared, I have explicitly declared internal wires S0 bar and S1 bar as coming out of the NOT gate outputs. Okay, so I am just instantiating the first NOT gate using the keyword NOT. The username is label is NOT1, and the output of that is S0 bar, input is S0. Similarly, the next NOT gate, NOT2 is the label, S1 bar is the output, and the input is S1. Now it is time to instantiate the 4 AND gates. AND is the keyword, AND1 is the label, the output is net1. You can see here the inputs are I0, S0 bar, S1 bar. So repeat it for the other 3 gates also with different names. Not like this, you can name it as AND2, AND3, AND4. I just purposefully kept it because if you write like this, it will give you multiple instance error. So though you are instantiating the same AND gate, all the time you give it different value. The first AND gate, if it is AND1, the next AND gate must be AND2, third AND gate should be AND3, fourth AND gate should be AND4, and so on. So according to what you have labeled in the circuit, let there be a one-to-one correspondence. So you have finished creating this output. So similarly, the first AND gate output is net 1, means second AND gate input should be net 2, third AND gate input should be net 3, and the fourth AND gate input should be net 4. Okay, so this is what we should map here. Then finally, once we have net 1, net 2, net 3, net 4, we are ready to create an OR gate. OR is the keyword, OR1 is the label. Then the first port will be recognized as the output port. Then whatever ports you are writing, that many number of port inputs will be that many number of inputs that particular gate you are instantiating will be having. So here you have 1, 2, 3, 4, 5 ports written here. The first port will be taken as the output port. The remaining 4 ports will be taken as the input. Net 1, net 2, net 3, net 4. So to do this, you must replace here net 2, net 3, net 4. Don't forget it. You are done. You can write the N module. So that's also in this particular session we have seen the different design styles in Verilog. As a summary, we can see there is an behavioral model or algorithmic way of writing. Then there is a data flow model which describes how data flows between different registers. Then there should be a gate level model or otherwise a structural model, and the fourth one is switch level model, which we haven't seen because it's not really in practice because of the complexity of the circuits we are dealing with while we are using hardware description languages. So we have seen examples, both a 2:1 multiplexer and 4:1 multiplexer written in different styles. Yeah, you may attempt all these things in the simulator as will be explained in the demonstration videos. Thank you.